Do you remember that in the previous section we talked about spinning? The idea that you continue waiting on something, but you don't give up your position in the schedule. You don't yield to other threads to only be rescheduled later on. Instead, you're just wasting CPU cycles. So there is a construct called a spin lock, which does something similar to the kind of locking that we've seen previously, but it does it using the spinning mechanism. And it also introduces us to another interesting idea or interesting problem called lock recursion. So that's what we're going to see now. Now, what I'm going to do is I'm going to change the example. So I'm going to get rid of the synchronization code here. I'll just set it back to what it was before. So I'll set it to the balance plus equals amount and balance minus equals amount. And then we'll actually synchronize access at these locations. So when we call deposit and withdraw, we're going to synchronize things here, and we're going to do it using a spin lock. So here it is, a spin lock. SL equals new spin lock. So this spin lock is going to help us control access to the variables, or indeed to the invocation of these functions. So how do you use the spin lock? Well, essentially we're going to have a variable lock taken indicating whether we were successful in acquiring a spin lock. So the idea in the previous examples was that you would always get stuck on a lock and you would always have success acquiring it. That's not actually 100% accurate, because a lock construct is just a shorthand for something else. It's a shorthand for the invocations of monitor enter and monitor exit. And the interesting thing about this is that in addition to an ordinary lock having monitor.enter, you also have something called monitor.tryEnter. And this is a lock mechanism, but with a timeout. So you can wait for a specific amount of time. And if you cannot get the lock, for example, you've deadlocked or something, then you just pass through. You don't execute the construct at all. So let's do the same thing inside here. So that should hopefully explain why there is a variable, a Boolean variable called lock taken. So we say var lock taken equals false to begin with, and then we try and acquire this spin lock. So we say try sl.enter, and we provided a reference to the Boolean variable indicating whether we were successful in taking the lock or not. If we were successful, then we can actually deposit the money. So let's put this in here. So if we manage to get the lock, we deposit the money. And then finally, once we're done, if we did in fact take the lock, then we exit. So we release the lock. Now let me once again explain what's going on here. So up until now, we basically assumed that a lock would always succeed, whereas that's not really the case. For example, if you have two different operations trying to take each other's locks, they'll deadlock and your program will freeze. So essentially, we have these mechanisms of failing to take a lock. You try to take a lock using sl.enter, but once again, you might time out, something might go wrong, and you will fail. In this case, we have a Boolean indicating whether you were in fact successful in taking the lock. And if the lock was taken, if you did take a spin lock, then you have to release it using sl.exit. So the spin lock, as I mentioned, is something that's going to basically spin the thread without yielding until you are able to execute. And we'll do the similar thing for the other method. So the other task is going to withdraw. So I'll put withdraw here. All right, so this is the same operations as we had before, but using a spin lock. So let's actually execute this. All right, we're still getting the balance as 0, which is what we want to get throughout all of these examples, or just about every one of these examples. Now, there's one thing I want to mention, which is called lock recursion, and it's actually a bit of a pain point, shall we say, in terms of operating on locks. And I'm going to get rid of this example so that we can look at a simpler, shall we say, example. So let's have, once again, bool lock taken equals false, and then we'll try, and I'm I'm not even spinning up a separate thread. We're going to do this on the main thread. I'm going to try and take the lock. Let's say SL dot. Okay, we need to actually make the lock again. So var SL equals new spin lock. Okay, so what I'm going to do is I'm going to try and take the lock more than once. And this typically happens in recursive setting. Let's actually do this differently. Let's have a separate static method. Which is going to be called, let's say, lock recursion. And we're going to take some integer, and we might want to, let's say, modify that integer, or actually this is going to control the depth of the recursion. So here I'm going to call lock recursion with a value of 5. So what we're going to do is we're going to essentially just try and use a spin lock. So bool lock taken equals false, and then we'll do a try where we try to enter the lock. Once again, I need a spin lock. So spin lock SL equals new spin lock here, and we're going to try and entering it. So SL dot, it has to be static, of course, SL dot enter ref lock taken, and then failing that, we'll actually take a look at what kind of exception we're going to get in just a moment. And then finally, we're going to check whether the lock was taken. So if the lock was in fact taken successfully, then we can notify, we can write line, for example, that we took a lock and x is equal to the value of x, and then we can recursively call the whole thing, lock recursion x minus 1. So we're kind of recursing until x hits 0. And then SL.exit, actually we're recursing forever. There's no limiting condition here. Otherwise, we'll console write line, and we'll say that we failed to take a lock, x is equal to the value of x. Okay, so I have a try catch here. Presumably I'm expecting an exception. So this is yet another thing that has to be explained, and it is this argument. So there is an argument specifying whether the spin lock should enable thread owner tracking. Now, depending on whether you set this argument or not, you're going to have information about which thread actually locked the particular spin lock. Now, this is particularly relevant in cases of lock recursion, because if you don't specify this, then a recursive lock, meaning you take a lock and then you call the function again and try to take that lock without it being released, will cause you to deadlock. Whereas if you do specify a true argument here, then you're going to catch exceptions, and the exception is going to be of type lock recursion exception. So here I'm just going to write line exception and then the body of the exception like so, and let's actually execute this and see what happens. Okay, so as you can see, we only managed to take a lock when x is equal to 5. Once we took a lock here, we went all the way down to here, and we recursively called ourselves, and we tried to take another lock on SL. And because the spin lock does not support lock recursion, we essentially got an exception, and that's the exception that you were seeing just a moment ago, this exception. So the takeaway from this example is that lock recursion is a problem. If you already took a lock on something, then taking another lock might not be possible. On the other hand, other constructs do support the idea of recursion, but generally the takeaway should be that recursion is dangerous. It's very difficult to control who took a lock and when you're calling a function recursively, or indeed when you're just repeating these statements in a very kind of complicated or convoluted logic. So that's certainly something to watch out for.